So till now we have done the SDE part. We have just uh, like simulated this SDE tool and we have seen the results of it. Now we will try to add the SDevice tools and find out how to find out that how to get the SDevice command files. So for that, let me add this tool first. So here we need a file for this SDevice tool. So for getting the file, there is a tutorial site from where we will take help. So for that we will type in Google Sentaurus TCAT training or tutorial. So this is the site coolguide.com. You have to click on it, and this is the main menu bar where you will get different modules like tool overview, Sentaurus Workbench, Sentaurus process, IC Workbench, Sentaurus topography, Sentaurus interconnect, Sentaurus structure editor. We have done this part. Sentaurus mesh. You will go through all these modules and you will able to find out that this is just tutorials. By following these modules you will be able to design your device. So today I am going to take help of this Sentaurus device, and these section contains basics, carrier transport model, mixed mode. So in basics, let's see what the things are there in basic section. So in basics it contain overview, command file and parameter file. So this is like in overview, Sentaurus device is a numeric semiconductor device simulator capable of simulating the electrical, thermal, optical characteristics of various semiconductor devices. It simulates 1D, 2D and 3D device behavior over a wide range of operating conditions, including mixed mode circuit simulation combining numerically simulated devices with their compact modeling, which is performed on SPICE based circuit simulation level. So this is the overview, and it can simulate these 1D, 2D and 3D. But in our case we are we have designed the structure of 2D for simple PN diode. So our task is to find a command file for the SDevice tools. So for that, this command file contains file section, electrode section, physics sections, plot sections, math section and solve sections, right? So what is in file section? So in file section it has input files like grid, nmos underscore mesh tdr, mesh.tdr. So this one is the like SDE command files. So this grid is act as a input file in SDevice tools, right? And next is parameter, then output files like current, plot and outputs. So these are the file sections. Next is electrode sections, where we have to define the electrodes, like in our case the anode and cathode are the electrodes. Then in this manner we have to define those. Next is physics sections. Physics sections it has different physics to be solved. If I tell you, like electron mobility, doping dependence, recombination, SRS, all those physics can be solved, should be there. So let's look at the transport model of this file. So came to module menu and carrier transport model. So here you can see in physics section it has Fermi, effective intrinsic density, mobility, doping gap, electron high field saturations, hole high field saturation, recombinations. So this is the physics sections, and we will copy this physics section for MOSFET, but we have like we have a diode, so we can copy some of it, and or one thing we can do, we can define this physics section by your or by your own self own. So as this command file contains file section, electrode section, physics section, plot, math and solve section. So let's write the whole master file from the scratch. You have to do it only one times. So electrode, let's say electrode sections where we need. So I will write electrode, and it contains in curly brackets, so we need to do it under this. And after that you have to name these electrodes. So for naming that, you have to put it in curly brackets once again. So write just name equals to, and then voltage equals to the value. Let's say I'm putting it 0 volt. And let's say our device contains, like as per now we know our device has only two electrodes, anode and cathode. But in if we forget that what is the electrode name, then you can visualize the on those portion by just using this SDE tool, visualize, then select mesh TDR, OK. Then come to lines and particles, and you can see here there are two anodes and cathodes, like here. So these are the contacts, anode and cathode. So these are the name, and it is case sensitive, so you have to keep the format same, like anode. And this is the repetitive thing, so I will just copy it and paste it and change the name of anode to cathode for this. And one thing you can do, you can put the resistances also. So I will put some resistance in series with these electrode. Resistor equals to, let's say 100 ohm, and next resistor it will be 100 ohm also, equals to 100 ohm. So this is the electrode section that we have done. Now next section will be a physics section, you can say. Section, let's copy it from a example file. Let's say getting started, then SDevice here, and there must be some file like transport model, you can see here. Okay, so right click on it, then edit input commands. So this is the like file. So here you can see this is the file section for this. Let's copy it totally, Control C, right, and paste it here, Control V. So these are the file grid, plot, parameters, and current output. Like this grid file is the input file for this SDevice tool, and .tdr is mentioning like it tells about the SWB sections. Like if I once again open it, so TDR mentioned that whatever the node available to left of this left of that file, like if you are using TDR in this file section, it means it will input the file from this SDevice tools, because it is left side of that's the thing. So grid file is the input file for this SDevice tools. Plot section is like this TDR dat. So this grid file contains the doping concentrations, like geometry and all those things. So that's why it plot those electric potentials, so those things. That's why it's extension stdr dat. Next thing is parameter. It is about like material things. Material parameters are something like current plots, just like inspection things. We measure the current voltages, cv of that, so current plot. And output is log, like it is in log formats. So all this is all about file sections. And in swb workbench, this is in this master file, if you put hashtag, then it act as a comment. So for a while I am commenting this parameter file, and rest thing will be uh, as it is. So we have done file section, electrode section. Next thing will be physics section. Section is solve section. So I will type solve, and it will be under curly brackets, and then I will do the coupled thing. See, coupled, and then in small brackets it will be iterations equals to 200. So and I want to solve Poisson equation, right? Okay, so Poisson equation will be in curly brackets, so let it be in curly. So initially this solve section, iteration means it will solve the Newton equation till 200, means it will solve the Poisson equation. As our anode cathode are initially 0 volts, so it will solve the Poisson equation in at 0 voltages. That will easy for it. And it will solve the Poisson equation, continuity equation, both. Then after that I will again couple these things for hole and electron both with Poissons. So I will copy it and then paste it, control V. Then I want to solve the Poisson equation along with electron and hole also. So I will type electron and hole. So it will solve the Newton equation till iteration equals to 200, and Poisson with electron and hole, and it will consider the electron and hole and solve the Poisson and continuity equations, right? It means continuity equation will be like recombination and generation things will be there. Charge and quasi Fermi levels are also there, so it will solve those things, include those things. After that I will give a quasi stationary QUASI STATIONARY. Quasi stationary initial steps should be like initial step let's say it is 0.001 equals to 0.001. Then min step let's say it is min step equals to 0.1 e minus 5, like 1 e minus 5. And max step will be max step equals to, let's say 0.01, right? Max step will be like this. And after that I will give it a goal, like goal in curly brackets, it will came. I want to vary the anode, so I will name it, and name equals to anode. Then voltage will be like voltage equals to, let's say, 2 volt. I want to give it, right, 2 volt. Then again I have to couple it, right? So for that I will just couple it again. So in curly bracket it will came coupled, and then Poisson electron hole, right? So make it in curly again. Poisson electron and hole. Okay, so this is the thing. Save it. Up quasi-stationary. Quasi-stationary means you go to the steady state and do the calculation, do the simulation. You are perform the measure the currents, those things. So it means quasi-stationary means it is a static state, right? So if you, while during simulation, if you reach this mean step 1e minus 5, then it means it will not converge and your simulation will be failed. So this is the initial step. Let's add increment and decrement in this process. Why we need to add this, I will tell you in a while. Decrement equals to, let's say, 2, and increment, so increment equals to, let's say, 1.5, 1.3. So when during simulations it tried to convert the values and to 0. If if during that moment if it is not possible, that it is not converging to 0, then it perform the increment or decrement string to get that results. So that's why we do this thing. Let's run the simulation using this only file, and surely we will get some output, but not the accurate one. So let's first save it and then try to simulate it. So I will come here and just try to run it. So it is showing some errors. So let's check undefined models or use math to escape this. So it is saying like there are some, okay, I think this one is not our, okay, let's open the master file first. Okay, so this one is not our, which, okay, okay. So this was the our file. So let's run it first. Like if I open this input, so this one is the file, right? We have to run it according to this file. So first I'm going to run it. So current status is running. You can see the color is, you can close it and double click on it and see the things are being done here. Okay, close. Current currently it is being run. So I think yeah, it is done now. We can visualize it. Right click on it, visualize, then plot. Okay, so we need to choose anode, outer voltage x-axis, and total current y-axis. So this is the IV of the our device. Why it is so accurate? And we have not used the physics, right? Oh, like we have simulated these by using the file, electrode, and solve section, and we get some values of the current. Now we have to activate the physics section also, in which we want to plot the Fermi, SRS, Eiger, electron mobility, hole mobility, and we want to plot the density and currents, electric field, and doping profiles, band to conduction band energy, valence band energy, all those things. So these things should be in the plot section, and physics should be here. So, and after that you have to you add math sections. You can copy these command lines from the example files provided in the SWB environment. So these are the things, and after saving that we can run it. So for that, just click and run and visualize. So it will take some time for that, and after simulation, this is the we can characterize the IV of these simple diodes, and we can see the potential space charge of this device. So that is all about this, and we have work in SWB using STE and SDevice tools, and we know how now we know how to get the command master command file for STE and SDevice also. Okay, so this is the process. Think the solution is being solved, yeah, here. Yeah, it is now done. Let's visualize this. So as it contains two files, PLT and TDR file. So in PLT file we will able to find the IV of the device, and in TDR file we will be able to see the band gaps and potential. So let's select the both, select all, and OK. So first let's see the IV of the device. So for that you have to click here and click anode, outer voltage x-axis, total current y-axis, and this is the IV of our diode. Next thing is, let's visualize the band gaps and other like potentials and other things. If you click acceptor concentration, or let's see electrostatic potential here, so you will be able to see the electric field, electrostatic potential in this device like this. Let's see space charge in this device. So this is the space charge, total concentration like this, current density, and and quasi-Fermi potentials like this. So let's make a cut on this axis, y cut, and see the different plots here. I can make a big screen to this. So currently we are seeing quasi-Fermi potentials. Let's say band gap, if band to band generation, conduction band energy like this, current potentials, donor concentrations, correct, doping concentration, electric field x-axis, electric field y-axis, space charge, you can see total concentration, valence band energy, right, conduction, you similarly you can use conduction energy. So all these are the like plot sections. Whatever you want to plot, you can mention it, and here from here you will be able to see. So if you want to see the band gap, so just plot band gap and click OK. It will plot the band gaps for you, right? This is the conduction band energy, this is the valence band energy, and these are the quasi-Fermi levels in the device, right? So this is the thing, this is the IV, this is the like quasi-Fermi potentials in the device, and this is the band gap. So I hope this is the thing. This software contains a lot of things to do. This is just a simulation of PN diode, PN junctions. So thank you so much. Bye bye.